In this section today, we're going to be discussing diprotic and triprotic acids and what happens with these guys when they react in solution as far as pH is concerned. What kinds of things do I have to remember? What things do I have to be aware of when I'm trying to count pH for these kinds of acids? Well, first of all, what is a diprotic acid? Well, di means two, and so a diprotic acid just means that it is able to donate two hydrogen ions. So an example of a diprotic acid would be H2SO4. If it donates its first hydrogen ion, you're going to be left with HSO4 minus, and it donates its second hydrogen ion, you're going to be left with SO4 2 minus, okay? So it's got two hydrogen ions it can donate. This just says that it's going to donate all of the first one before I have to worry about that second one being donated. H3PO4, phosphoric acid, is an example of a triprotic acid because there's three hydrogen ions there that it can donate. Okay, so you're going to knock off one at a time, and it's going to donate all of the first one before it starts donating any of the second one. Okay, so the problems here, they are long, but they're not that hard. You just have to keep track of everything that's going on and make sure that you're thinking through it logically, okay? So again, just because it's long doesn't mean it's hard. So don't look at that huge blue text box and go, I can't do this. Yes, you can. You can do it. You just have to keep everything straight. And I'm going to show you how to use these ice tables that we've talked about before to make sure that you're keeping everything straight as we go through the process. All right. So in example 7.8, he says 1 mole of sulfuric acid is dissolved in a liter of solution. Now, if I dissolve 1 mole in 1 liter, that makes my concentration 1.00 molar. Moles divided by liters is molarity, okay? Then he says, then 0.750 moles of solid NaOH is added. The solid does not affect the volume of the solution appreciably. It's important that he says that because if you start dumping solutions together, then you've got to keep in mind what the volume is of the solutions that you're adding. We did some KSP problems that were that way, where you added a couple of solutions together and you had to say, okay, that changes my concentration. Here, we're not changing the volume, so the solution is not going to be changed that much. So I can still assume 1 liter of solution. So then for my NaOH, I'm also going to have 0.750 molar in solution there. Okay. What will be the resulting pH? And he gives me the Ka of HSO4 minus, which is the conjugate base of H2SO4. All right, so first of all, I'm just going to start out that, plain and simple, I just have a stoichiometry problem to deal with. So I'm going to have H2SO4 plus NaOH, okay? Strong acid, strong base, complete reaction. So I'm just going to donate, remember our rule up here, we're just going to donate one at a time. So when this reacts, I'm going to have HSO4 minus plus, this breaks up into a sodium ion and a hydroxide ion. So I'm going to have a sodium ion, and this hydroxide ion is going to go with this hydrogen ion that was donated over here. So I'm going to have water. All right. Hopefully that wasn't too difficult for you to write. So when I think about this, again, it's a complete reaction. So at the beginning of the reaction, I have 1.00 molar here. I have 0.750 molar here, and I don't have anything on this side of the reaction. But it's a complete reaction. So after the reaction is over, from what you can tell here, all of this is going to get used up. So there's not going to be any of this left over. And that's going to give me 0.750 molar concentration of this and 0.750 molar concentration of the sodium ions. And of course, water, we're not concerned about that. But I still have some H2SO4 left. If I've used 3/4 of a mole of it, then obviously I'm going to have 0.25 moles left over. Okay, so there's the first step. I still have strong acid left, and so the water that's in solution is now going to start reacting with the H2SO4. So I'm going to have H2SO4 plus the water. It is still a strong acid, so it's still going to react completely. And so what that's going to give me is HSO4 minus plus H3O plus. Okay? So when I have that, I now need to look at what I'm starting with. So for the H2SO4, I have 0.25 molar here, so that's before the reaction takes place. I had 0.750 moles from this first reaction, so before the reaction ever takes place, I have that much HSO4 minus, and I don't have any hydrogen ions because I didn't make any up here. Because remember, all the hydrogen ions that were given off reacted with the hydroxide and made water, so I didn't have any. Okay, so that's where I am before the reaction takes place. After the reaction takes place, all of this acid gets used up because it's a complete reaction, so I have nothing left over here. I'm going to add 0.25 moles to everything on this side. So if I add 0.75 plus 0.25, I'm now up to 1.00 moles over here, and I'm going to have 0.25 moles over here. Okay? Now what happens? Am I done? Well, it would be nice if we were done, but we know that HSO4 minus is a weak acid, and it's now going to react with water. The first two were easy because here I just had strong acid, strong base. Here I had strong acid with water, so both of those are complete reactions. But now I've got this HSO4 minus, and it's going to react with water, but because it's a weak acid, I'm now going to have an equilibrium set up. So this is going to give me SO4 2 minus plus H3O plus. Okay, so here again, I need to evaluate where am I and where am I going with this. So initially, what is my concentration? So at the end of this reaction before, I had 1.00 here. Okay, water doesn't matter. I didn't have any sulfate ions, so I didn't have anything here, but I did have some hydroxide ions to start with. I had 0.25 here, so I need to put that here as what I started with initially. As the reaction, as the equilibrium gets set up, I'm going to lose X here. I'm going to add X to both of these sides. So at equilibrium, this is going to be 1 minus X. This is going to be X. This is going to be 0.25 plus X. Okay, so that's where I am at equilibrium. So now I need to take the Ka that I was given and I need to set that up. So my Ka equals SO4 2 minus times H3O plus over HSO4 minus. That's just from the balanced equation up there. I was told that the Ka is 0.012. At equilibrium, the sulfate concentration is X. The hydronium ion concentration is 0.25 plus X, and the HSO4 minus is 1.00 minus X. Okay, that's messy. Obviously, it is extremely messy. He says in his explanation, as he works this out, he says, we could try to make a simplifying assumption and hope that X is really small. However, I'll just tell you it's going to be wrong. I have a PhD. You have to believe me. Well, even people with PhDs can make mistakes. So how do I know that he's right? Well, if you remember all of the problems that we worked in module number 6, we knew that that simplifying assumption only works if this number is really, really, really little. And it's not that little. It's not like it's got a magnitude of 10 to the minus 5 or 10 to the minus 7 or 10 to the minus 13. This is only 10 to the minus 2. And so that's why he says it's not going to work. And indeed, it will not work. You're going to have to work it all the way out, use the quadratic formula, because you can't ignore this plus x and this minus x. Now, I am not going to take the time to work out the quadratic formula because that is algebra, and I am assuming that if you are in advanced chemistry, you are perfectly capable of working out the quadratic formula from here. Okay, so you're going to work that all out. Once you solve the quadratic formula, you are going to find out that x is equal to 0.040. Okay, now, what does that mean? Well, that's what x is. What is it we were trying to find? Because sometimes we get so lost in what we're doing that we get lost. We forgot what we were trying to do. Well, we were trying to calculate the pH. The pH is the negative log of the concentration of the hydronium ions. Well, is that the concentration of the hydronium ions? No. The hydronium ions is 0.25 plus x. So my hydronium ion concentration, from what I learned from this reaction, is that this is 0.25 plus x, so that's 0.25 plus 0.040, and then when I add that together, that's going to give me 0.29. Remember, use your addition rules for significant figures there. So that's 0.29. Now you can take the negative log of this number. And so then if you take the negative log of 0.29, now you're going to be able to come up with a pH, and you're going to have a pH of 0.54. Okay? Okay. Yes, we just filled up the entire dry erase board with one problem. Okay? But again, just because it's long doesn't mean it's hard. You've done all of these pieces before. You just have to keep the pieces separate in your mind so that you know what you're doing. Okay? So I started out with a strong acid, strong base reaction. I still had some strong acid left over. The strong acid reacts with water, again, in a complete reaction. Then, once the strong acid is all gone, then I take the conjugate base and I'm going to set up an equilibrium with water, and this is going to act as an acid now. I use my ice table in order to calculate equilibrium concentrations, use the Ka expression to go from there. Hopefully you have a nice problem where you can use these simplifying assumptions, but if you don't, it gets messy and you got to use the quadratic formula in here. And then from there, you've got to make sure that you go back and say, okay, is my hydronium ion just X? It wasn't in this case. You got to make sure that you add this other piece to it. And that actually came from the strong acid a couple of steps back. So make sure that you keep track of this when you're calculating the final pH. All right. What about if I just have, what if I have a triprotic acid? How complicated does that get? Well, a lot of times it's not necessarily as bad as you would think. So I'm going to show you how to work example 7.9. And since I don't have any more space, we're going to erase this. What you will find is that a lot of times the Ka for the secondary acid that you get after you lose the first hydrogen ion in a diprotic or a triprotic acid, sometimes that Ka is so small that compared to the hydrogen ion concentration that you already have, you don't even have to worry about it. And in fact, the rule that he gives you is that if the conjugate weak acid is 20 times or more weaker than the original, that you don't have to worry about it. You don't have to consider it. So let's look exactly and see what that means. So we're going to look at example 7.9. And example 7.9 says, what is the pH of a 0.5 molar solution of phosphoric acid? So we're going to do what we did before. We're going to say, I have H3PO4, Thankfully, I don't have a base to deal with this time. So that does make this problem a little simpler from that perspective. Phosphoric acid is not a strong acid. So initially we're going to have an equilibrium set up. So I'm going to react it with water. We're going to set up an equilibrium. I'm going to have H2PO4 minus plus H3O plus, okay? You set up your ice table. Initially, the concentration of the H3PO4 was 0.50 molar. And so I wouldn't have anything over here. I'm going to lose X here. I'm going to add X in both of these over here. So at equilibrium, I'm going to have 0.50 minus X. This is going to be X, and that's going to be X. Okay? The Ka, the equilibrium expression here is H2PO4 minus times H3O plus times H3PO4. They tell me that the Ka is equal to 7.5 times 10 to the minus 3. H2PO4 minus is X. H3O plus is X. H3PO4 is 0.50 minus X. Is this one small enough so that I can ignore that? No, I already have two significant figures here, and this just goes one more place out, one more decimal place out. So I got 2 places after the decimal point. This is in the 3rd place after the decimal point. So the chances of this being small enough that I can ignore it are really, really small. And if you would try it, you'd find that it doesn't work. So again, you're going to have to use the quadratic formula in order to solve this equation. And once again, I'm not going to go through all that because you know how to do that. When you solve this, though, you will find that X is equal to 0.058 and X is the same as the H3O plus here. So that's my hydronium ion concentration. Now, do I need to worry about the fact that they told me what the Ka of H2PO4 minus is? Is this now going to dissociate and add even more hydrogen ions? Technically, yes, it will, but the Ka is so much smaller that I don't have to worry about it. So that the first Ka they gave me was 7.5 times 10 to the minus 3. And then the next one is 6.3 times 10 to the minus 8. I got those two numbers from the problem. So if you look at the problem, you can see the 2 Kas that they gave me. If I take this number and I multiply it by 20, the answer I get is still much, much, much smaller than this first Ka. So if this answer is smaller than this after I multiply it by 20, I know that I do not have to worry about it. It's going to be so small that the amount of hydronium ions that it adds isn't going to make any difference. And so therefore, this is going to be the final hydronium ion concentration that I have to worry about. So I can take the negative log of this number, and I'm going to have a pH of 1.24 for this solution, okay? So again, the way that you can tell if you need to set up yet another equilibrium is, can you take the second Ka, multiply it by 20, are you still smaller than this one? If you are, then you don't have to worry about the next equilibrium reaction. You can just ignore it, which is what you always hope for, because then you're done, right? Exactly. So I don't want you to get frustrated with these problems. Remember that all of the pieces you have already done, all of the separate pieces, we're just putting them all together, and you have to think through logically as to what's happening with the reactions as you go through each problem. Okay?